So the first kind of side channel attack that we're going to discuss is something that's called flush and reload. And if you understood how we are able to determine if a value was in the cache or not in the cache, in that original example, just with that timing data, start time, end time, if you understood what was going on there, you already understand the bulk of how flush and reload works, because it's based upon those same mechanisms. We're just taking it up a notch a little bit as far as what we're looking at, and we're applying a creative intuition as far as what does it mean for a value to be stored in the cache. Now, before we can get into kind of the details of flush and reload, let's talk about some of the kind of lower level primitives or lower level functions that we can use to influence the cache layer. So in the prior lecture, we had a diagram where we showed the layout of a particular CPU. And the CPU had multiple cores. Within each core, there were 2 hardware threads. And then we saw that there were caches that were associated with specific cores. We saw L1 and L2 caches that were core specific, and then a large L3 cache that was shared amongst the cores. Now, depending upon what cache layer we're interacting with, we may need, it may be a requirement that a program stays on one core, because we want it to always be interacting with one specific cache. Or maybe we have 2 programs that are going to be interacting with each other via a cache layer, but we need both of them to always be interacting with the same cache layer. Well, we can force this to happen by pinning the programs to a specific CPU core or a CPU thread. And we do this with the C function schedSetAffinity. Once this function is called, that process will not be able to be migrated off of that core to another one, regardless of how busy the core that it was assigned to gets. It's just going to have to deal with the congestion and busyness of where it has decided to be pinned. And so this is a powerful thing that we can do to ensure we know where in hardware, like where physically on the computer, are these assembly instructions being ran, which is necessary for these kind of low-level interactions to occur. Now, another thing that we saw was getting timing data. We weren't using libc's getTime. We were using this __ RDTSC, this kind of read timestamp strange function. Well, this is a low-level, high-precision counter value that is representative of time that we can get directly from the CPU. And since we are measuring time inside of the CPU, the most accurate counter we can get, the representation of time, is going to be the counter that is inside the CPU. So for all timing data, we call RDTSC. Now, another thing that we saw happen was evicting data from the cache. I said, well, we can call this mmclflush function. And I passed it a buffer address, right? It was the beginning of this array. And I said, this will flush the buffer from the cache. And we didn't know if the buffer was in the cache. We just called this CLF or CLFlush function, and which is short for cache line flush. But we called CLFlush, and that flushed the cache entry from the cache. How does that work? Why is there an address? Well, if we think about the size of these cache layers, we saw there were cache layers in the size of kilobytes, and I think there was an L3 cache in one of the diagrams that was in the order of megabytes. These caches can actually be quite large, and so it doesn't make sense to clear the entire cache. Instead, it makes sense to evict specific entries that need to get removed. Now, why would we need to remove them? Well, maybe there is an atomic operation, or this is a volatile value, as far as like, why would this practically be needed? And we don't want the CPU to ever access older data. And so caching data means that we run the risk of getting outdated data by touching the cache. And so you may want to flush a specific region of memory from the cache so that whatever is obtained is always fresh and correct, whatever is the actual status in RAM. And so this address value is a hint of where in virtual memory am I trying to flush. Now, we saw that these cache line entries had a fixed size, right, depending upon the hardware. On the Dojo, that happens to be 64 bytes. If I were to pass an address of hex 1000 into this CL flush function, it would flush from hex 1000 to hex 1063. It would flush 64 bytes from that location. But what happens if I pass in the address of hex 1005? Well, the cache is still aligned by 64 byte increments. So it would still flush that same entry. It would flush the entry that is from hex 1000 to hex 1063. It would be those same 64 bytes that are evicted. And so when we pass in an address that isn't telling the cache where to start evicting, it is evict the entry that happens to contain this address. Now, this has some interesting implications when you're thinking about, is something in the cache or is something not in the cache? Because what if the value is larger than 64 bytes? Well, maybe I need to call CL flush twice because I need to cover both sides to make sure that I'm evicting any cache entries that cover that larger value. And so to evict a larger value from the cache may require a for loop that is going to loop over every 64 bytes of this larger value and call CL flush. And you want to make sure that the order that you are calling these CL flushes are 64 byte aligned. Occasionally, you may see the compiler start a struct or start a particular value at like a strange offset due to padding or alignment, or a struct is extremely tightly packed. And so like you have a address that is at some weird offset, like 1000, hex 1003. You need to be aware that the cache entries are evicted in 64 on the Dojo are evicted in 64 byte kind of chunks or entry chunks. And so you need to account for that when you're trying to evict a larger value or like a larger array. Now, for all of these C functions, there are corresponding x86 assembly instructions. These C functions are really just super lightweight wrappers around these low-level assembly functions. And so these are kind of functionally equivalent. And we'll see that as we go through the module. Now, another thing that is worth kind of talking about is something that's called a fence. So we talked about how we could influence caching. We saw that in the last lecture video. How do we influence speculation? Well, we influence speculation with something that's known as a fence. And what a fence does is when a fence function is encountered or a fence assembly instruction is about to be executed, the CPU will stop speculating and it will wait until we've kind of reconciled with reality to some degree. Now, the degree to which reality must, be correct and make sense depends upon the fence that we use. Now, if we require all speculation to be reconciled and we need everything to be true as far as what is the value of memory, then what we want to use is an M fence. An M fence causes speculation to stop at this point and cause all of the stores to memory and loads from memory to be reconciled with reality. And then we will continue execution. Now, that sounds great, but you have to think about this very similar to like if we were to use a semaphore in a multiprocessor, multi-threaded program. The more semaphores you add, or the more times that you cause kind of this synchronization to occur, the slower your program's going to run, because you're causing all of these pause points for synchronization to occur. So in the interest of performance, it may not make sense to use an M fence. Instead, maybe we're only interested in loads from memory into the CPU. If that was the case, then we would use an L fence. And that would cause speculation to stop at that instruction until all loads from memory have returned. We're not going to guess at what the loaded value is. So all of the values that we're computing on at that point are real. Now, if we're more interested in the stores to memory, then we would use an S fence. And that means we're not going to speculatively store anything to memory. Instead, we're going to wait at this S fence until all stores are in fact real. We aren't going to march ahead and speculatively continue execution. Now, we kind of had this concept of thinking about exploits as primitives in the later half of this class, or what are the requirements to perform this exploit. And we saw this in a number of the prior modules, but we can use that same logic here when we're thinking about this side channel attack or caching. What are the requirements for a program to influence caching in an interesting manner? Well, there has to be some target or some program or some value that I'm interested in. And this is our target, right? And the way that's a target value in any kind of meaningful way gets placed into the cache is if it is accessed, right? We said that's how we put things into the cache. And so there needs to be some program or some memory region that we're interested in that is the target. And so we need to be able to influence the target's execution so that we can get the target to either perform an action that may or may not interact with the cache, and then we're going to observe the state of the cache. And so what we want to do is very similar to kind of that initial example from the prior lecture. The difference is that instead of me observing my own accesses, I want to observe the accesses of another program or another function, right? Something that isn't my own code. Because if I can observe values in the cache that were placed by somebody else, I may not know what the value of that address is, but I can know that that address was accessed by a target, by a specific program. And that has intrinsic meaning, right? That conveys information via a side channel. So I need to be able to somehow, influence the target's behavior to some degree, right? To get it to perform an operation that I'm going to observe the impact of. I also need to be able to access this memory region that's used by the target. And that makes sense if you think about what I just described. We're going to have some type of target function or target execution, target program. It doesn't matter. There is some execution that is going to either touch memory and put something in the cache, or it's not going to touch memory. Well, how do I observe that? Well, in order to observe that, I need to be able to query that same memory address. It doesn't mean I need to know the value of it. I just need to be able to query it, because what I'm interested in isn't necessarily the value. It's how long did it take to access that memory address? I'm still interested in timings, right? And so I'm trying to access a memory region that is used by the target. And so we could be looking at a scenario where the memory region that we're interested in checking, is this in the cache? Is this not in the cache? Well, where does it exist normally? Well, it could be in the exact same process, right? What if I was running shellcode? Well, my shellcode would be interested in accessing memory of whatever it is I've injected shellcode into. But what if I have two different processes? Well, there could be shared memory. You could have a page of memory that physically is one page of memory, but it gets mapped to two different processes. For instance, if you have a read-only page, what will happen is there's one physical page of memory, but the virtual memory there may be multiple virtual memory addresses, and since it's read-only, when they go through the translation of going from virtual memory to physical memory to find where in the RAM is the actual value, these virtual memory addresses can point to the same page in physical memory. It's a great optimization that you have with that virtualization or virtual memory abstraction. Now, where else could this memory region be? Well, this memory region could be kernel memory, right? The kernel has the ability to map. You could mmap into the kernel, or the kernel could mmap some region of memory from user space. And so you could have, for instance, a page of memory that is being accessed by both the kernel and by user land. And so the requirement is, can we influence the target's, and it says execution, but it should really say behavior. Can we influence the target's behavior? And do we have the ability to access memory in a way where we can reason about the behavior that we triggered? As far as the specifics, where is that memory? That doesn't matter. It's, can we influence behavior, and can we access a memory region to observe the impact of that behavior that we triggered? And that's how we can use caching as a side channel. So let's walk through this process in a more visual manner. So we said the first step is to call mmcl_flush on the target addresses, on the locations that we're interested in. So we have some victim assembly function, and just looking at the victim assembly, there's a branch where we either access memory or we don't. And so what we're trying to figure out here as the attacker is what happened at this branch. And the first thing we have to do is we have to flush the addresses that we're interested in. Well, the address we're interested in that tells us the piece of information we want is this RAX plus hex 20. And so if I know the address of that, we can flush that address. We can do that. And that would flush it from the cache. Now, once that value is flushed, we trigger the behavior. We want this victim assembly code to run. And so the victim assembly code starts running. And the victim assembly code performs its comparison. Maybe the branch goes this way, and the victim does access this memory address. Well, when the victim accesses the memory address, it goes all the way out to memory. It's going to put the value in the cache before it comes back into the CPU to get into RAX. That could happen. But what happens if the victim does not access this address? If the branch goes the other way, and so this comparison is not equal, then we're going to jump to this skip label. And so if we jump to skip, the cache didn't change. And so once the victim code has ran, the attacker can now try and access that memory address that it's interested in, that it was very fixated on. And so we're going to start a timer, and then we're going to try and access RAX plus hex 20, which is some value that we know. And so when we try and access this memory address, what's going to happen? Is it going to go out to memory and take a long time? Is it going to go out to RAM? Or is it going to touch the cache and come back real quick? The answer tells the attacker what happened in the victim assembly code. And this is that kind of clever intuition about what does it mean if something is in the cache. Because we have an idea of what the victim assembly looks like, we can apply a context to whether or not this cache entry exists or doesn't exist. The cache entry tells us what happened at this branch. And so when the attacker performs this, they can time their own independent access. If it's long, then we know the cache wasn't filled. And so we know what happened in the victim assembly function. If the attacker tries to access this and it's short, well, then we know that the value was in the cache. And if the value is in the cache, we know what happened in the victim assembly to cause that virtual memory address to be stored in the cache. And so it's applying meaning to something being in the cache or not in the cache. And that is kind of the key insight to flush and reload. Again, very similar to kind of that initial demo, just showing that we can measure it. And so there is a lot of crazy going on, but conceptually, what we're doing here is pretty straightforward. Now, there's a couple challenges that we can certainly run into. And one of the mechanisms that is separate from speculation that will influence values in the cache is something called cache prefetching. This is commonly found in, for instance, for loops. The CPU can detect that a for loop is occurring, that you're iterating over a region of memory, and it will start to fetch ahead of time values that it thinks will be needed next. And so if you write a for loop that is accessing memory that you're trying to control, whether or not it's in the cache, the prefetching mechanism of the CPU will actively work against you. So how do we solve this? Well, instead of writing a for loop that the CPU can detect, we need to mangle our for loop, typically through a bunch of like bitwise operators. We're going to XOR, we're going to AND, we're going to OR it. We're going to perform some type of mangling that isn't easy for the CPU to understand what's going on. And if the CPU can't understand what's going on with our indexing, then the CPU won't be able to recognize a pattern, so the CPU won't be able to prefetch these values and load them into memory. Let's take a look at a quick demo of kind of that functionality in action. So on the left-hand side, I have a C program. We have a victim function this time. Our victim function is just loading a value into memory, and it is some index times the cache line size. And cache line size is some value that's larger than 64, some multiple of that. Okay, and that's all we have for the victim code. For the exploit code, I've condensed this down so that we don't kind of get lost in the noise. We have a post work function, and that's the only thing that's pulled out. Otherwise, this looks very similar to what we saw with kind of our own measuring. There's some pre-work that's going to occur, and then this victim function is going to get called. This victim function is going to take a value from argv and store it in a volatile character. And then we don't do anything with it. So we're just accessing memory, right, based upon this index value. And so what do you think's in this pre-work? Well, the pre-work is going to be flushing the cache. All right. And so then we print, we're done with the pre-work. The victim function runs. We print starting post work, and then this post work function is called. Now there's two lines here in post work. What is post work doing? Well, post work is doing some type of looping over a buffer, right? There's an array, there's some region of memory that we're interested in. And we are doing some inner work on every multiple of this array. So like every 64 bytes, we are probably performing some type of timing, right? We're accessing it and measuring the access here in this inner work. Because what we're trying to figure out is, what did the victim function access? And there's two lines up here for mix I. And this is the only change that we're going to make between two executions or runs of this program. In the first one here, mix I will be I. And so this is going to function just like a normal for loop. It's for I equals 0, I is less than buff size, I plus plus. I'm just going to iterate straightforward through this array or region of memory that I'm interested in. And let's see what happens. Demo 2.1-C. And let's give it 2. Oh, wow. So there's a lot of data coming out here. And if we look at these values, well, I gave it the index of 2. Is 2 significantly different? The timing here of index 2 significantly different than any of the rest of these that happen to be a lower value? The answer is no. And I could run this again. Okay, we got lower values, but they're all lower, right? And so there isn't anything unique. There's no value that particularly stands out that would indicate what the heck is going on here with victim function. Why is this occurring? Well, the CPU can detect that this is a for loop and that we're looping over some region of memory, right? We're just iterating our way forward. And so the CPU, the prefetcher, is grabbing these values ahead of time and loading them into memory. And it's doing it in our post work. So in the pre-work, we may have flushed it. But now that we're down here in the post work, because we're in a detectable for loop, the CPU is going to start putting things in the cache to try and optimize performance, because that's what the CPU is focused on. It doesn't care that we are interacting with the cache. It cares about how it can use the cache to run faster. And so this is pretty useless from a side channel standpoint. Now, if I comment out this line, and now I do something weird. Now my mix I value, instead of being 0, then 1, then 2, then 3, and going in order, I'm going to multiply it by 167. I'm going to add 13, and then I'm going to AND that value with 255. Now, the exact mechanism will depend upon what values you're trying to loop through. You'll have to come up with some kind of masking equation that will make these still touch every index that you're interested in, but in a mangled and kind of messed up order that the CPU can't understand. So let's see what happens if I use this new mangled method of accessing and doing my inner work, my timing on these memory addresses. So let's compile this again. Okay. And let's run it with 2. Well, that is a world of a difference. 2 is the only value that is below my threshold. Because in my post inner work here, not only am I doing this measurement, but I'm only printing out values that are fast, right? If the timing of accessing something was long, I don't want to print it out because I'm not interested in that, in this context. And so now it doesn't matter what I put. I have pretty much 100% accuracy on predicting what index this victim function accessed. And the reason this works, again, to stress it, is because I am changing, I am mutilating and mangling this index value. There still is a for loop, and it's going through this. I is iterative. Well, what is being passed to post-work, inner work? Some mangled value. And so when the CPU looks at this, it can't make sense of it, and so it doesn't try and load anything into the cache because it doesn't know what to load into the cache. We want to make sure it's confusing so that the CPU doesn't try and hurt us by trying to help us. Because remember, the CPU is trying to optimize. And so if we make this so messy that the CPU can't optimize it, then we have control over the cache in this regard. And so that is kind of how the prefetching mechanism of the CPU can work against us when we are trying to influence the cache. So what other challenges exist if we're going to try and perform this flush and reload attack? Well, in addition to prefetching in the CPU, we also have to deal with the realities of physical memory. Because remember, when we're trying to do this like microarchitecture exploitation, what we care about is what is occurring in the actual hardware more often than not. And so what we kind of care about here is what is going on with physical memory. Because it's physical memory that is memory access that is trying to be optimized by the CPU. Right? It is the literal request across the circuits and that request time. The virtual memory is just an abstraction to us as a process. Now, we don't get to interact with physical memory. We have to interact with virtual memory. And this creates kind of a unique scenario where there can be some lies that the kernel will tell us, and some may help us and some may hurt us, but we should be aware of some of the things that we may encounter. Because we can only interact with virtual memory from within our kind of exploit process. The first thing that I'm going to mention is that repeated virtual pages may in fact be backed by a single physical page. So why would this occur? Well, what if there are multiple processes that are all trying to access the same read-only page? Well, if it's the same read-only page, there's no reason to duplicate it in physical memory. But the kernel can still return a unique virtual address to every process that requested it. And then during the translation phase of virtual addresses to physical addresses, they can all resolve to the same place. And since it's read-only memory, it's never going to change, and so no one's the wiser. And it optimizes that physical memory usage. Now, why is this interesting to us? Well, let's think about it from a caching standpoint. If I have two processes, even though they're accessing different virtual memory addresses, those two virtual memory addresses that are in fact different may be referencing the same underlying physical page. And so the cache hits may be related despite the fact they aren't mapped the same in virtual memory, but it is the same underlying physical memory. And so that can create an interesting scenario. Now, another thing that I'm going to claim here is that mapped memory may not be backed by anything at all. The kernel will just lie when pages are mapped. And the kernel will return a virtual memory address that has no physical memory behind it when mmap is called. Now, how does the kernel get away with this? Well, if the process doesn't touch the memory, then the process isn't any wiser, and the kernel didn't have to deal with physical memory. So that's an optimization. But what happens if the process actually uses the memory, like a sane process would? Well, when that page is first accessed, right, it's first written to, this causes something that's called a page fault. And a page fault triggers the kernel to suddenly reconcile that virtual page with physical memory. So it's kind of like oh no, the process is touching this page that I told it had, and we need to suddenly figure out where does that virtual memory address translate to in physical memory. And so it's not calling mmap that causes physical memory to get allocated. It's this page faulting and writing to it that causes memory to actually get consumed by the system. Now, I have a demo that kind of shows this. It's a little bit different than the existing code that we've seen, because it's really just to show that virtual memory can lie to us. And what we have here is a main function where argv1 is going to get stored in this size variable. We're then going to printf about to mmap whatever size gigabytes. We then do that in a loop. So we're going to repeatedly mmap 1 gigabyte at a time. We'll then output proc self map. So we should be able to look at these mappings that mmap returned and find them in the process mappings. The program will then block and ask touch pages. Once we say yes, it's going to loop through most of those pages, and it's going to start writing values to these pages. And my claim is that we can mmap a ridiculously large amount, and it won't cause any changes to the system. However, once we start writing to all these virtual pages that we were given, that is when we're going to start putting real constraints on the system up until the point where the system could actually just kill us for exhausting resources. And if we manage to make it all the way, we will output our mappings again. So what I'm going to use here is the watch command. And this will give us every couple seconds, it's going to update, and we'll see what is the available and free. Now, the number that we're going to be watching here is the free swap, because that is what we will be impacting. So let's compile this, demo 2-2. We'll run it. Now we see we have about, 7.5 gigs. So let's do 20. So that was quick. We were able to mmap 20 gig. We have 20 pointers here. These all should be about a gig of mapped memory. And if we look at the memory addresses, where are they? Are they mapped? Well, 7F B2F00880. Yeah, okay. So this most recent mapping is right after the heap. So this is looking like everything is working as we would expect. But we didn't see any changes here to like the available memory or the free swap. Now we're about to start touching these pages. We're going to start dirtying them. And every time that we write a value to these pages, that is going to cause a page fault. And as these page faults rack up, we are now mapping these virtual memory addresses to physical memory addresses, because the virtual memory facade, it has been lifted, because now we're actually using this memory. We mmapped 20 gig and we don't have 20 gig. That wasn't a problem. But now we're trying to touch 20 gig worth of virtual memory and write stuff across this 20 gig space. And we see that the swap value is decreasing and decreasing and decreasing. Now, once this value approaches the terminal 0, something is going to happen over here in our process. And what we see once we get there is we're killed. We're killed, and the system reclaims its 7.6 gigabytes of free memory. But it wasn't a problem for us to mmap 20 gig to begin with, which is quite interesting. So we need to have some idea of how virtual memory and physical memory relate. So now that we've talked about some of the challenges that exist while performing a flush and reload, let's talk about what the flush and reload actually is. Well, it turns out we've been doing kind of flush and reload this entire time. We were doing flush and reload back in lecture 1. Remember, the steps of flush and reload are flush the cache, run the victim code, do some timing, compare the timing. Well, how did we determine back in lecture 1 whether something was in the cache or not? We were performing these same steps. So flush and reload is something that we've already been doing. Here is the first example of this lecture. The only difference is that I've pulled out some of the implementation details so that we can take a look as far as what is going on in detail. And so to recap, the argv1 is going to be turned into an int as an index. That index is going to get passed to a victim function. The victim function is going to use that index to access this buffer array. And it's going to access the buffer array in such a way that every index will result in a unique cache line entry, because this is accessing the array in multiples of some number that is larger than a cache line entry size, so larger than 64 bytes on the dojo. So what are we doing? Well, our work is the pre-work and post-work. This is where the exploit is occurring. So let's look at pre-work. What is pre-work doing? Well, pre-work is zeroing out this memory region before the victim function runs. This has two effects. Sure, we're writing 0 to this entire array, so we know the value is 0, but that isn't necessarily what we want to be doing here. What we want to be doing is making sure that we're accessing this region of memory that we're interested in. Why are we accessing the region of memory that we're interested in? Well, by writing to it, if this was virtual memory that wasn't backed by anything, when we perform this memset, we are writing to that entire memory region. So if there are any pages that aren't backed by physical memory, this will cause a page fault and ensure that they do exist, because we want to make sure that the memory region that we are working with does exist in physical memory, that it is backed by something real. So then what else are we doing in our pre-work? Well, we are looping through the buffer and calling CL flush. Well, unlike the first example in lecture 1, the buffer here is larger than 8 bytes. This is some large buffer. In fact, this buffer is larger than a cache line entry. Because remember, a cache line entry is only 64 bytes on the Dojo CPU. And so if I want to make sure that this entire buffer is not in the CPU cache, I need to call CL flush repeatedly. I need to call CL flush at the beginning of the array. I need to call CL flush 64 bytes into the array. I need to call CL flush 128 bytes into the array. I need to loop through this and call CL flush for every 64 bytes of the memory region that I'm interested in. That's the only way I can ensure that this entire buffer is not in the cache. Because you can only flush cache line entry sizes. And so every MLCL flush is only flushing 64 bytes. So that's the pre-work. Again, it's not a ton of code, but it's very important that it is correct. Now, the victim function runs. At this point, pre-work made sure that the cache was not accessed. What is happening in the victim function? Well, the victim function accesses something in that buffer. And the act of accessing will create an entry in the CPU cache. So then in our post work, what's happening? Well, the post work is going to perform this loop. We're going to be looping through the buffer. But we are doing this mix-I, this weird mangling. What's this mangling doing? Well, the mangling, if you'll recall, is preventing the CPU prefetcher from identifying that we're in a for loop and adding entries into the cache, because the CPU wants to try and optimize performance. So if we make our index mangled in such a way that the CPU cannot understand that we're in a for loop, it can't predict what the next I is going to be, then the CPU will not be modifying the cache by adding entries. So then we do this post inner work. Post inner work, what do we have going on here? Well, we take the index, we compute an address. We're then going to call time access no flush. What's time access no flush doing? We're getting the cycle count from the CPU. We are performing an access. We have a fence to ensure that this syncs. We get the cycle count again, and we compute a time equivalent from this. So we're timing our own access. Once we have the time for a particular index, we check if it is below some threshold. And this is just a threshold that I chose based upon what I saw in the timing data. If it's below the threshold, then the entry is likely in the cache. So if we compile this again, we've seen this, but I just want to show that it is in fact the same code. We get the behavior that we would expect, where we are able to predict the value that is being passed into the program via the cache timings. That index value from argv to index to the victim program is never getting passed to right here where this print is occurring. We are detecting it via the side channel that is the CPU access. So flush and reload isn't that complicated on the surface of it. There's just a lot of challenges and factors that you typically don't think about when you're working in a higher level programming language, or even when you're working in assembly. We have to think about how the hardware is going to behave. Now, while continuing this discussion on how the hardware behaves, let's take another quick detour and revisit prefetching. So we said prefetching occurs because the CPU can identify that we're iterating through an array or a region of memory, and so the CPU will try and optimize performance by loading values into the cache ahead of time. And in normal operation, this is a fantastic improvement for performance. However, when we're trying to measure access times of the cache, we do not want the CPU putting new values into the cache, which would mess up our analysis. But prefetching is useful. So aside from the CPU deciding to just prefetch values all on its own, prefetching can be triggered directly via assembly instructions or via a C wrapper function. Now, why would we ever want to invoke prefetching directly? Well, in like a hyper-performance situation, it may make sense to provide a hint to the CPU that these memory addresses are going to be needed. Let's load them into the cache ahead of time, so that way when we do access it, we know it'll be a quick access because we're going to touch the cache. In these instructions, you can even specify the cache layer that you want to access. So you can say, I would like the values at this memory address to get stored into the L2 cache or the layer 2 cache, or I want it to be stored in the layer 3 cache. Now, the specific cache that you may want to target will depend upon the CPU architecture. We saw in the prior lecture a diagram of one particular architecture where L3 was shared across cores, where L1 and L2 were not. And so you would need to be aware of the architecture that you're trying to target when you're determining what cache you want to target. Now, ultimately, this instruction is just a hint. And so the CPU may completely ignore it, right? We could be like, I want to load everything into the cache, and the CPU can just say, I'm not doing that. And so we need to keep that in mind as well. Check out the link below for the assembly instruction that is used for prefetch. But if we think about prefetch a bit more, this instruction is still going out and accessing memory. It's very similar to when we try and dereference a memory address in assembly. What does prefetching have to do? It has to take a virtual memory address, it has to translate it to a physical memory address, and then load the data from that physical memory into the CPU's cache. And so this is a kind of mechanism or a step that takes some amount of time, and we can measure the time of the prefetch instruction. And by measuring the prefetch instruction, we can actually gain some information about the virtual memory address. So we have a quick demo here where we're going to time prefetch instructions and see if we can figure out what it is that we can learn about virtual memory via prefetch. Okay, so for a demo here, I have a C program that's a little bit different than what we've seen already, but let's run through it. The first thing that we're doing is we're calling mmap. We're mapping a page of memory. We're then going to write to the beginning of that page. Why are we writing to that page? Because remember, mmap returns virtual memory addresses that may not be backed by physical memory. By writing to the page, I am ensuring that this virtual memory address is backed by physical memory. I'm going to print off the pointer that was returned by mmap so that we have it. Then I'm going to loop through some memory. I'm going to start 10 pages behind that pointer, and I'm going to loop 10 pages after that pointer. I'm going to loop a page at a time. For each one of these pages that I'm accessing, I'm going to print the address followed by a measurement value. And this measurement value is computed by this repeat measure function. Repeat measure, as the name kind of indicates, repeatedly calls measure. It calls measure 10 times and is summing the value. So what's going on inside of measure? Well, remember, this is a timing attack. We can't directly observe prefetching, but we can observe side effects of it, like metadata, like how long it takes to run. So if we're measuring the time of prefetch, how are we doing that? Well, we're going to use that same pattern that we've seen with fetch and reload. I'm going to call RDTSC to get a timestamp value. I'm going to have some fences to prevent speculative execution. I'm then going to perform the call that I'm interested in. So I'm going to try and prefetch whatever that pointer value is. And so we're going to be prefetching about 20 addresses here, 20 different pages, and then measuring the time of it. And so for each page, we're going to try and time the prefetch 10 times. And then we're going to print that out. Also note that the program is blocking because we're going to do some kind of program introspection here before it's all said and done. So let's compile this. See if I can type today. All right, warnings are suggestions. And when we look at the program output here, we see kind of what we would expect. We get a bunch of memory addresses and we get a bunch of measurements. Now, it's worth noting here that there's clearly like a jump right off the bat that I notice. There's this series of pages that are coming in around 700 as far as that summed number. And then there's this series of pages that are averaging around 1,000. So that's kind of interesting. Why is that happening? Well, before we kind of delve into that, let's look at our mmap value. Well, the mmap value was 7582000. So let's find that. Looks like it's right here. And so the mmapped value was a small value. And we see several pages later is where this jump to long values, where prefetch took a long time occurred. So what is going on there? Well, we need to get some context. What are these virtual memory addresses? Right? I need some context to reason about, well, what am I trying to prefetch? And we can do that by looking at the mappings. So this is the mappings for this program, because remember, this program's still alive. It's just blocking, waiting for me to provide it some input. So where is my mmap address? We said 7582000. So let's take a look there. I see it 7582000. So our mmap pointer is right here at the beginning of this region. So then if we look at contiguous memory after this, because remember, we're going forward in memory and just iterating by a page at a time. We see 8300 is here, 8400 is here, 8500 is here, and then 8600 is kind of the end of this block of memory at 758600. If I were to try and access 758700, then there would be a seg fault if I were to try and access that memory directly. So what is going on? Can I use that information over here? Well, what I see is 8500 is valid, right? 758500. And then once we get to this edge of memory, it jumps up and takes a long time. And we shouldn't be able to access that, right? This isn't like 7587000 is invalid virtual memory. It isn't mapped anywhere in this process. If we were try and grab the value from there, we would seg fault. But I can try and prefetch it. And so this is a way of trying to access a memory address that may or may not exist. And we can determine whether that virtual memory address exists based upon the timing. If we go back here, look at 75, the first one. It was 10 pages behind. 755A. Does this exist in virtual memory? Well, we said that we started right here. So 755A is somewhere here. Is that right? Did I get it? Let's take a look. What is that? 7F49. 7F4F. 7F4F9755. So we're up here. 55A00. So it is the edge right here. The very first address that we're checking is valid memory because it's going to fall right there, which is mapped. And so what we see here, or we can kind of infer, is the prefetch instruction is quick if the virtual memory address exists, and the prefetch instruction is slow if the virtual memory address doesn't exist. And this is happening in the hardware. It's the hardware that's doing that access. So we don't segfault by doing this prefetch on invalid virtual memory addresses. So again, we have a timing side channel that is conveying information that we otherwise couldn't get.